Good evening, everyone. I'm very happy to be here to introduce my previous work about CRISPR-Cas system. My title is The Construction of CRISPR-Cas12 and CRISPR-associated transposase system in E. coli. My work contains two parts. The first is CRISPR-Cas12 system. The second is CRISPR-associated transposase system. The CRISPR-Cas9 system has been widely used in the gene manipulation of a variety of organisms, ranging from prokaryote like E. coli to eukaryote like a mammalian cell. The CRISPR-Cas9 system contains two parts. The first is the Cas9 protein. It's a CRISPR-associated endonuclease can recognize the PAM and act as a molecular scissor to cut DNA at the location specified by guide RNA. The second part is sgRNA. It consists of CRISPR RNA and trans-acting RNA, which can bind to the Cas9 protein and specified based on the sequence of the gRNA. With the development of biotechnology, many novel CRISPR-Cas systems has been and characterized. The CRISPR-Cas12 system has smaller size of Cas effector compared to Cas9 system. It's expected to be widely used in the gene manipulation of mammalian cell. Besides, the PAM of Cas12 is very different from Cas9. Cas9 protein prefers the NGG PAM, while the Cas12 prefers the TTA and TTG PAM. So we want to reconstruct the CRISPR-Cas12 system in E. coli. So we synthesize the Cas12 gene and the gRNA and clone them into the PSTV28 and PUC57 to construct these two plasmids. To test the cleavage activity of CRISPR-Cas12, we designed 3 spacers targeting the histone gene of E. coli and insert them into the p-target plasmid. Then co-transform this plasmid into the E. coli. We can see this picture. From the picture, we can see the cardinal number of these 2 experimental groups decreased sharply compared to control group. So this may indicate CRISPR-Cas12 system can access the E. coli genome with high efficiency. We want to construct a convenient tool to make gene editing in E. coli. So to improve the recombination efficiency of E. coli, we insert arabinose inducible recombinase into the plasmid. Then we introduce ribose inducible sgRNA, which can targeting the AMP promoter of p-target F. So we can use this gRNA to cure the p-target F. To assist the removal of pCas12, we replace the original replication origin with a temperature-sensitive replication origin, so we can cure the pCas12 after editing and transform our production plasmid into the E. coli to make products. So the pCas12 plasmid contains 4 parts. First is a temperature-sensitive replication origin. It can be used to cure the pCas12. Second is a ribose-induced sgRNA. It can conditionally express the sgRNA targeting the AMP promoter of p-target to cure the p-target F. The third one is a PRPSL-driven Cas12. It can express Cas12 constitutively. The fourth one is arabinose inducible recombinase. It can conditionally express the recombinase. To make the gene editing, we also need to construct a p-target X to specify the location. So we can see the plasmid profile of the p-target F. We pre-site 2 BSV1 sites at the plasmid, so we can insert our spacer at there. For example, this is a histidine gene sequence of E. coli. We find the TTG or TTA PAM first, and then select 20 nucleotides at the behind the PAM. Then design primers, anew the two primer, then insert at the between the two BSA1 site to construct the p-target X. The Cas12 protein can cut the DNA at the location specified by gRNA. If there is no repair template, the string will die from double-strand break. So we need to provide a repair template to help the bacteria survive. There are two methods can be used to prepare the repair template. The first one is overlap PCR. Using overlap extension PCR to select the upstream and downstream homologous arm and gene fragment. The second method is to construct a template plasmid. Then we can amplify the repair template from the plasmid. Specifically, we can, for example, we can amplify a 1 kb gene fragment from the genome and insert them into a plasmid. Then design two primers to amplify the whole plasmid. At the same time, we can make the multiple cloning sites. So we can insert our cargo gene into the plasmid, then use the two primer to amplify the repair template from plasmid. This is a protocol of using CRISPR-Cas12 to make gene editing. This is a protocol for removal of p-target and p-Cas12. To test the if we can use the CRISPR-Cas12 system to make gene editing, we design different lengths of repair template to make to knock out 800 base pair gene fragment. From this picture, we can see we successfully knock out the 800 base pair from the genome. This indicates CRISPR-Cas12 can be used to delete gene fragment using even shorter homologous arms, but no less than 100 base pair. To further investigate how large size of DNA can be deleted using CRISPR-Cas12 system efficiently, we conduct an experiment to delete different lengths of gene fragment. From this picture, we can see at least 6 kb gene fragment can be efficiently deleted using CRISPR-Cas12 system. Previously, we using plasmid as a vector, we have produced so many kinds of isopronoid in E. coli, but the plasmid expression is not stable. It cannot be scaled up. So we want to integrate the mevalonate pathway into the genome. The first step is to screen some integration site for gene overexpression. So we want to use the EGFP as an indicator to evaluate the expression level of this site. So we construct this p-target F plasmid and the template plasmid. We successfully integrate the EGFP gene into different locations of the genome, but we cannot detect any fluorescence in these strains. We don't know why. So to find the reason, we replace the EGFP with MVES at the PTSG and POXB site. After culture, we identified the presence of mevalonate in the culture medium. So there is still a lot of work to be done in the future. The second part.
Jan,
Yeah.
can you go back?
Okay.
So you show the graph left side, right side. Yeah, cellulose graph and mevalonate. So there's two bar. One is a white bar, the other is a pink bar. what does pink bar means?
This one,
Pink.
P.
Yeah.
P-
So white bar is
it-
36 hour. Then what is the
it's 48 hours.
48 hour?
Yeah.
Okay. And you failed to see the GFP's expression.
Yeah.
So that might be the problem of EGFP gene. We